So here's our first theorem, and it was pretty surprising to me at first that this is a theorem and not an axiom. So part 1, this is called symmetry for equality. So this property of equality is called symmetry, that if x equals y, then y equals x. And remember, there's an implicit universal. So it's saying it's not, while the x and y are free here, it's not specifically trying to be about x and y. It's saying in general that if two things are equal, then if you flip around that equality statement, that's also true. The second one is transitivity. It's called transitivity for equality. This property is called transitivity. So if one thing equals a second thing and the second thing equals a third thing, then the first thing equals the third thing. So let's discuss the proof. To remind you what the word theorem means I'm about to write down a proposition, and I'm claiming that the proposition is true, meaning has a proof. So when you see the word theorem, usually you see the word proof coming soon afterwards. Now, this theorem doesn't look like a proposition immediately. It looks like a list. It's a numbered list. But that's just a fancy or just more nicely organized way of writing an and. So it's a conjunction. It's saying this number 1 here holds and number 2 here holds. That is a proposition. And actually, let's just focus on the proof of one of them. So I'm going to focus on the proof of part 2. So I'll only do certain proofs in lecture, so I don't put too much video on you guys to watch. And I'm trying to choose things that are useful to narrate a little bit. Okay, so my goal is to prove this implication. This is an implication. So I should assume the left side and then try to prove the right side. All of this stuff that we learned about in the logic section using placeholders for propositions is stuff that we can still use and we should be still using. So how should I prove an implication? Assume the hypothesis and then try to prove the conclusion. So then, assume that x equals y and y equals z. Now my goal is to prove that x equals z. Okay, well, I don't have much that I can use, so when you're very early on doing very early theorems, things are both easy and they're hard. They're easy because there's not that much that you can use, so you don't have many options for what moves you can make. And so anything that has a proof is not going to have a very complicated one if it appears early on as something with a reasonably sized proof. On the other hand, things are very hard because, again, you have so little that you can use, so you're missing a lot of tools that you might be used to having in a different context. Okay, so what do we do? Can I make use of axiom 1? I mean, I can always use axiom 1 if I want to. I can be like, yeah, x equals x, y equals y, z equals z. But how's that going to help me reach x equals z, which is my goal? I've got to use axiom 2. And axiom 2, sort of, like I said before, is kind of an axiom scheme. It's a factory that generates axioms based on what proposition phi I put in place of that placeholder in axiom 2. Okay, so let's go off to the side here for a moment. So remember that our goal is to prove x equals z. But let's go off to the side here for a moment and think about how we want to apply axiom 2. So I am just going to write in some things here and be right back. Okay, I've set it up kind of like a recipe here. So the ingredients that we need to apply axiom 2 to a particular situation is we need somebody to play the role of x, a y, someone to play the role of phi, someone to play the role of a, and then here's the recipe. Just make sure that x equals y, then axiom 2 allows you to deduce this. Okay, so for us, remember we're over here, we are assuming x equals y and y equals z, and we would like to prove x equals z. So here's, after thinking about it for a while, here's something that ends up being helpful. So we're in a situation where we know that our x actually does equal our y, right? Back here, we do actually have x equals y. So let's have x play the role of x, y play the role of y, and for phi, well, we want to prove y equals z. So I'm going to choose the proposition a equals z, and you'll see how this pans out, how this works in a moment. And then I've chosen the letter a here, so a can play the role of a. Then I'm in a situation where x does equal y. Then what does axiom 2 let me deduce? It lets me deduce x equals z if and only if, and then this says y equals z, which is also something I have in my situation. So all of this scratch work here that I have done to carefully apply axiom 2, I'm going to go back to the proof and summarize it like this. I'm basically just going to say, by applying axiom 2 to the proposition a equals z, we can conclude that x equals z if and only if y equals z. So let me write that in. So by applying axiom 2 to the proposition a equals z, we can conclude, and actually before I say we can conclude, I should also mention this important fact that we're applying axiom 2 to. It requires us to have x equals y, so by applying axiom 2 to the proposition a equals z and the fact that x equals y, we can conclude that x equals z if and only if y equals z. Alright, great. So now, since y does equal z, since y does in fact equal z, we have x equals z. So what I'm using here is this idea. I have the equivalence that x equals z if and only if y equals z. And a way to use an equivalence is it lets me know whether one side is true based on the other side. Their truth is linked, right? So knowing that this one is true tells me that this one must be true. It's both arrows, basically. All right, and I've reached the goal. I've proven that x equals z, so that's it. I'll put my square here to end the proof of part 2 of theorem 3. Part 1 also has a proof where you have to go over here and apply axiom 2 to a particular situation to try to prove part 1.